Thanks so much for coming along. So this is our event titled Why You're Not Dead, Biomedical Science. I'm Libby, I'm the coordinator for York Biomedical Research Institute. So again, thank you so much for coming. It's great to see a nice full audience and a range of people here. It's a pleasure for me to introduce our event today. There is a QR code here if you haven't had a chance to scan it, just to have a quick look at our website and learn more about York Biomedical Research Institute as a whole. I'll give you a little insight and then I'll hand over to the real stars of the show, which are our students. So, YBRI is a virtual institute situated at the University of York, and we aim to provide an internationally competitive, multidisciplinary research environment and high-quality, fundamental, translational research into biomedical and clinical sciences. And then in the Institute, we also have a biomedical sciences programme, a lovely banner over there that tells you a little bit more, and another QR code. So we have an MSc by research and also a PhD programme. All of our speakers today are on the PhD programme. And this programme in particular provides an opportunity for outstanding graduates with an interest in biomed, the area of basic science which focuses on the study of fundamental biological processes involved in health and disease. Spanning a wide variety of disciplines in the life and physical sciences, biomedical research employs cross-disciplinary approaches with the overall aim to understand and treat disease. Hence, the power of biomedical science, why you're not dead. So our speakers today will be presenting their work across our research themes. You can slightly see this banner here, which shows our research themes, which are immunology, haematology and infection, molecular and cellular medicine, and neuroscience. So we'll be starting off with Nathalia, who will be giving us insight into neglected tropical diseases. Zooming in a little bit more from a global view to a solid cancer view with George, who will be looking at bladder cancers. Zooming in even further to beyond the solid cancers into blood cancers, and Lizzy will be showing us how she's got a new hope for targeting cancer cells. And super close into the inner workings of the human brain, Diogo will be showing us how he's fishing for clues in neuroscience. So with that, I'd like to hand over to Nathalia, and with our first presentation of today, to Nathalia.
So hello everyone, as Lizzy has said, my name is Nathalia. I'm a first year PhD student at the University of York. And today I'm going to talk to you about neglected tropical diseases and a little bit about climate change. Before I introduce this topic a little bit further, I would like to introduce myself a little bit more. So I did not start as a scientist actually. I started as a nurse many years ago. And during my 13 years career, I actually worked with a wide range of conditions, as you can see here, from cancer to respiratory illnesses and genetic conditions. But for over 5 years, I was a clinical lead, specialized in the elderly and palliative care. But I have always loved microbiology, and in my mid-20s I met a researcher who was specialized in neurodegenerative conditions, and he got me really interested in what research was, and I decided to explore that as a career option. So that's why I went back to university. I did my second degree, which was in biomedical science, followed by a master's in microbiology, and finally here I am doing my PhD in biomedical science. So with regards to climate change and how it's affecting infectious and non-infectious diseases, so we know that because of Earth getting warmer, the transmission of diseases is actually changing, and that factors that contribute to that are things like, for example, farming and natural gas production. And that climate change, as I say, affects not only infectious diseases but also non-infectious ones. This, for example, we have people who suffer from asthma and COPD in areas where the air is more polluted tend to get worse. We are also now seeing more and more infections in our crops, like, for example, infections that affect food security around the world. And we are also seeing that the increase in temperature in the sea, as well as the decrease in the salinity, so the decrease in salt concentration, it's causing new infections of cholera in areas where before were never seen. So now, with regards to my topic, which is neglected tropical diseases, I can tell you they affect up to 1 billion people in developing nations. They cause around 200,000 deaths per year, and they are also the cause of 19 million cases of disabilities. Unfortunately, because we are seeing the temperature increasing, we are expecting to see more cases. You may be thinking, have I ever heard about neglected tropical diseases? And chances are you have. these are examples of some that you might have heard of. We start with the one on the left-hand side, which is leprosy. In the middle, we have a bite mark, which you might not see very well, but this is actually an animal that had rabies. And on the right-hand side, the one that I'm more interested about because it's a bite by a mosquito of the disease ISTD, which is African trypanosomiasis, also known as sleeping sickness or nagana in animals. So, as I say, it's transmitted by the bite of infected tsetse flies. And usually they live in areas like river shores and bushlands, but unfortunately, as the temperature continues to rise, we are seeing that they are moving around in all these countries, and they are now thriving in areas where before they were not able to. Unfortunately, the disease can be a little bit difficult to diagnose, and this is because it has very vague symptoms at the start. Luckily for us, the human form of the disease is very well controlled, and this is because in the 1960s, when this was a huge problem in Africa, all the governments came together and put together strong policies. And we have seen the cases coming down. For instance, at the early 2000s, we still have over 26,000 cases reported just in Africa, where now, towards 2020, there were less than 1,000. But unfortunately, that's not the case for the animal form of the disease, which continues to cause millions and millions of losses every year. Now, why I'm saying that the disease is difficult to diagnose? This is because when it starts first, it's really, really vague. I mean, a person can experience fever, pains and aches in joints and muscles, and also fatigue. And in all fairness, those are symptoms that we can all suffer during a normal cold. But as the disease progresses, then we start seeing swelling in certain areas. We start seeing people suffering from fits, even though they don't have epilepsy. And we also, at the end, we see people going into a coma and then actually passing away. So what is it that I'm trying to do with my research? We know that the parasite does have a complex life cycle, and it needs to live in the fly long enough to then be able to infect us. So what I'm looking at is actually how is it that this parasite can actually get into us and then travel around all our body and to our different tissues. We know that it's because they produce some substances, and that's exactly what I'm looking at. I'm looking at the role of these substances into invading our different tissues. Just to summarize everything I have said, as you can imagine, climate change affects us all. As we are changing the fate of our planet, we're also changing the fate of infectious diseases. And as scientists, as healthcare professionals, we do have a role in advances in our fields, but I have always believed that we are stronger together, and I'm hoping to be one of these people that help build this bridge so we can provide more approachable healthcare around the world. Thank you very much.
Okay, so hi everyone, my name's George. I'm a first year biomedical science student, just like Nathalia there. And today I'm going to be talking about bladder cancer. So I'm going to specifically starting off with an introduction to what bladder cancer is and how it's caused, before moving on to really kind of what is the peak of this cause and what is a massive dilemma in the field of bladder cancer, of how our change of understanding of the cause of bladder cancer has kind of dramatically changed. So when we say bladder cancer, generally what we're referring to is a disease known as urothelial carcinoma. Unlike all cancers, this is caused by an uncontrolled growth of cells in our body. Specifically in this circumstances, we're talking about the urothelial cells, so these cells that make up the lining of our bladder, our ureter and our proximal urethra. And inside each of our cells in the body, where you can think of them as having a rule book that tells them how to behave. And this rule book is full of many different rules. It's vastly complicated, but for bladder cancer, if we think about cancer in general, there's 3 rules that are really important. So the first of these rules you can see here is that only grow and divide when the bladder is damaged. So this means normally at health, at rest, our bladder isn't dividing, the cells in our bladder are kind of quiet, they're not growing. The second rule is what I'm calling as an error checker. This is, you can think of like your spell checker on Word. This allows cells to look at their rule book and look for any changes that might be leading them towards cancer and correct them. And then finally, very importantly for the survival outcomes of bladder cancer, is our invasion mode, which at rest in healthy cells is turned off. Essentially meaning our cells of the bladder stay in the bladder and aren't tempted to go wandering anywhere else. Now, as we progress through our lives, we're exposed to a whole variety of internal and external factors, and these factors cause changes to our rule book, which are known as mutations. So the first mutation that's important for bladder cancer is that our error checker is knocked off, and this leaves us in an incredibly vulnerable position where essentially our cells are unable to look for future damages that are going to occur to our cells, and this leaves them incredibly vulnerable to cancer. The next and probably the most important step in our progression towards cancer is a corruption of our growth signal. So our cells get damage in some way to their rulebook, and this causes them to begin to undergo uncontrolled growth. It pushes them towards classically what we define as a tumour. And it's at this point that we'd really start to define things as bladder cancer. Lastly is our invasion mode, which is knocked off. So this means that our cells begin to spread beyond the bladder wall, and this is where our outcome for bladder cancer really decreases. So I've just told you these mutations are causes damage to our rulebook and pushes us towards cancer. But what causes these mutations? So there's these factors here. So we have male sex, about 3 in every 4 bladder cancers occur in men. We have smoking, which makes you about 4 times more likely to be at risk of bladder cancer. There's aging, which is a massive risk factor for almost all cancers. And then these 2 at the bottom, thankfully, due to our strict health and safety laws, aren't so much as a problem. So that's occupational exposure, and I'm not going to try and pronounce that compound name, but we commonly see these compounds in traditional Chinese and Eastern European herbal medicines. Now, I appreciate that's a bit doom and gloom, so I do want to include some things that we can do to reduce our risk of bladder cancer. We can eat healthily, avoid processed foods, we can exercise, and we can reduce stress, which can be quite hard to do during a general election campaign, but we can try our best. So, I've just told you that mutations push us towards cancer and they cause us changes in our rulebook. But how do we actually know that one specific thing causes a mutation, right? How do we know? How can we say smoking causes mutations? Well, the way we do that is through these things known as mutational signatures. Now, these graphs look awful, but the colours, the bars, all that things are essentially irrelevant. The way we can think of mutational signatures, and we can look at graphs like this, is thinking of them as a fingerprint, as essentially a fingerprint that tells us specifically what the cause of cancer is. So this is a signature, this is signature 4, which we commonly see in lung cancer. Does anyone want to have a guess as to what might cause signature 4? Yeah? Smoking, yeah, spot on. And we see this throughout cancers caused by smoking. So once we discovered these mutational signatures, and we figured out we can look at what the causes of cancer are, we started to look at bladder cancer. And when we looked at bladder cancer, we found something really surprising. We found a signature 5, which accounts for about 30% of our signatures and is associated with aging. But the other 2 are our signatures 2 and 13, which surprisingly come from our response to a viral infection. And it was this discovery that really kind of blew apart the field of bladder cancer. For years we thought of smoking and industrial chemicals as being the risk factors for bladder cancer, but actually what the evidence from tumours is telling us is that it's actually looking like a response to a viral infection that's driving bladder cancer. So if most of our mutations in bladder cancer come from a viral infection, does a virus cause bladder cancer? More importantly, what virus is it, and how can we stop that virus? And that leads me on to the BK virus. So I could spend hours talking to you about the BK virus, but unfortunately I've only got a few minutes, so I'll just run over the basics. So unfortunately, basically everyone in this room will be infected with BK virus. It's about 95% prevalent in the adult population of the UK, but in almost all of those cases it's completely harmless. It causes a mild flu-like symptom as a child, and then it kind of goes away. But when we say it goes away, what it's really doing, what we believe it's doing, is it's sitting in the kidney, it's dormant, it's lying at wait. And for most of us, it will never reactivate. We'll never see any problems of BK infections. But where we do see problems is in kidney transplant recipients. So people that are placed on immunosuppressive medicines, when they undergo transplantations, become increasingly at risk of an active BK infection. And there's a recent study that's found that in kidney transplant patients who go on to develop BK infections, they face a 12 times greater risk than the average population of developing bladder cancer. Now, I'm sure there are probably lots of questions, but unfortunately I'll have to leave it there. I'd like to say thank you to York Against Cancer, who are the amazing charity that fund my research and the research of our lab, and do some amazing work with the cancer community, as well as to the University of York. So thank you very much.
So, hi everyone, my name is Lizzy. I'm a second year PhD student in biomedical science, and I'm going to give you an overview of my topic, which is battling blood cancers with a hope for a new way to target cancer cells. To start off with, I just want to give a general introduction to what is blood cancer. So, this is where something goes wrong with the DNA in your blood cells. So, imagine here, this is your DNA, and it's present in the nucleus, which is almost the brain of your cells. So when something goes wrong in the brain of your cells, therefore the cells become damaged, become cancerous, and things start to go wrong. And in blood cancers especially, this causes your body to become less effective at staying healthy and fighting off infections and generally repairing your body. And this is what leads to a whole host of symptoms that you see in blood cancer. such as fevers, sweats, early bruising, more frequent to other types of infections, and the list keeps going on and on. However, rather than keeping with you that, blood cancer is still a prevalent thing in the UK, unfortunately, with 1 in every 22 women and 1 in every 16 men will get it in their lifetime. That results in about 41,000 new cases a year. And it is still the 5th most popular cancer in the UK at the moment. And another thing to point out is that it's not only does it have gender disparities, not only is it more common in men, it also differs in different ages. So it's the most common childhood cancer with about 500 cases annually. However, it's also an aging disease. So about 40% of cases are prevalent in people aged 75 or earlier, or older, sorry. So it increases, incidence increases with age. But what I do want to point out is that actually blood cancer here in Yorkshire is quite interesting because it's very representative of the whole UK as a whole. This is because Yorkshire, as a county, has a similar ageing population, a similar female and male balance, similar rural and urban population, and socio-economic thing that is the same as what it's seen across the rest of the UK. Therefore, we can study blood cancer in Yorkshire really well. In addition to that, Yorkshire has become a bit of a hub for blood research. And this is something that I want to talk about. And the blood research here in Yorkshire is really great because we're working on focusing on new blood cancer treatments to improve these survival rates. You get more than 1,500 more blood cancer survivors each year, and this number is increasing. And this is due to the constant licensing of new drugs for blood cancer. And this is because we're switching from this type of first-line therapy, which is very toxic. This is radiotherapy and chemotherapy. And this is kind of toxic. You've got a lot of debilitating symptoms, and the treatments are not great in the long term. However, we are trying to shift, my research is shifting to this more targeted medicine. And this is focusing on using antibodies and your own immune system, and combination with other things such as surgery and bone marrow transplants to create a personalised medicine to you. And therefore, this is more specific to target only the cancer cells and not your other cells, with less harsh symptoms and better for long-term solution. So this is what I'm trying to do in my project, and this is a lot better. So to kind of show this, I just want to quickly show blood cell development. So this starts in a hierarchy of cells. So you have the queen of cells called the stem cell, and this starts at the top, and this has the ability for most power to split into any different type of cells. And the further you go down, you get the prince and the princesses, which can then split into 2 different pathways. So you have the first line of defence. So this pathway is involved is once you get something not normal in your body, such as something like a bacteria or virus or a cancer cell, it'll try to fight it off. And then you've also got cells involved in long-term protection. So this remembers when you have been infected to remember what the infection was and how it fought against it so it doesn't happen in the future. And these ones have killer cells, so they will fight off, protect, and remember by producing antibodies. On the other half, you have these cells which are more involved in initiating when you see the cells causing something foreign in the body, megakaryocytes that produce platelets to fight off clots, neutrophils that ingest anything nasty in your body that shouldn't be there, and red blood cells that help to survive and keep your body going. However, what I'm interested in is these kind of cells that are present throughout the whole hierarchy. But rather than these cells individually, I'm actually interested in something that is found on the outside of these cells, and that is a receptor. And a receptor is involved in signalling pathway with a signalling interactor. And what this means is the 2 of them come together and cause downstream kind of pathway that tells the cell what to do. It tells that brain of the cell what to do and decides the outcome. So, example, it may take a megakaryocyte to make platelets because that's downstream. So I'm really interested in this particular receptor found in all of these cells. However, what is interesting is when something goes wrong with this receptor caused by a mutation, damaging the DNA, when something causes a disease, this is where you get dysregulation and blood cancers. This is when your cells stop becoming healthy, and this causes so many different things, such as having too many red blood cells, too many platelets, and extensive scarring of the bone marrow. And what this causes is a whole host of blood cancers and symptoms So what I'm really interested in is there a way that we can target this mutation that causes this dysregulation and causes the blood cancers, and rather than trying to, and this would allow us to target just the cancerous cells. So I like to summarise my project using a train track. So imagine a train track, and here you see you've got multiple pathways. One pathway is to healthy signaling, and the other pathway is to dysregulation and general blood cancers. However, if you get a mutation that occurs during this healthy signaling and it's blocking your access to healthy signaling, and what you want to do, what I'm trying to do, is take the receptor that's found on these cells and see if I can do something to it, give a drug, a therapeutic, to this receptor that will alter the way it works and prevent unhappy, bad signaling, blood cancers occurring, and find an alternative route to achieve this healthy signaling by changing the receptor and changing the inside of that cancerous cell to make it healthy again. And this is what I'm trying to focus on. Thank you very much for your time, and thank you for dealing with my voice. And I'd like to thank everyone at the CBR, and I'll happily take some questions later. Thank you very much.
So my name is Diogo, I'm a PhD student at the University of York, and I'm going to be telling you a bit about my project, Fishing for Clues in Neuroscience. So, as a neuroscientist, I study the brain. More specifically, I study white matter. But what exactly is that? So, this is a brain cell. A brain cell has to communicate with other brain cells and with the rest of the body. And it does this with electricity. So, it carries an electrical impulse from this side all the way down to here. Much like the charger you use to charge your phone. And just like that charger, it needs some type of insulation. So for a charger, it would probably be some type of rubber or something like that. For a brain cell, it's not rubber, it's a substance called myelin. But it does pretty much the same thing. It protects the brain cell and it keeps the electricity in. This is what white matter is. Now, however, sometimes this white matter can become damaged. And when this happens, just like with the charger, if the rubber is gone, the wires are exposed, you won't be able to charge your phone. With the brain cell, the brain cell will lose the ability to communicate with other brain cells and with the rest of the body. And this is exactly what happens with leukodystrophies. So, leukodystrophies are a group of inherited disorders. This means it's a disease you're born with, that you inherited from your parents. Now, there's many types of leukodystrophies, and while individually quite rare, altogether they account for 1 in every 4,700 births. That means in the UK alone, 130 babies are born with a leukodystrophy every single year. So, like I said, as the brain cells lose the ability to talk to each other and with the rest of the body, patients experience a progressive loss of motor function. That means they lose the ability to walk, the ability to speak, the ability to swallow. When it manifests in childhood, unfortunately patients normally die before the age of 5. When the disease manifests later on in life, that normally happens 10 to 15 years after diagnosis. Despite being a fairly common and very severe disease, there's next to nothing we can do for the patients at the moment. And that's why we've set up Leucolabs. Leucolabs is a network of research labs here in the UK dedicated to study and understanding leukodystrophies. This was set up in partnership with Alex, the Leukodystrophy Charity, or Alex TLC. This is a charity dedicated to help patients and their families with leukodystrophies. This was set up by a woman called Sarah Hunt, a single mother, after both her sons were diagnosed with leukodystrophies, and the charity is named after Sarah's older son, Alex, who unfortunately passed away in 2012. So this is the vision of Leucolabs in partnership with Alex TLC. We hope to be able to identify new patients and then use our network of research and all the tools we have available to us to quickly identify new diagnostic tools so we can identify these patients early and develop new treatments, which hopefully will have a positive impact on patients. So, as a member of Leucolabs, I do some of this research, and for that I use the zebrafish. So this is a zebrafish. It's named after its characteristic stripes, and it's about the size of a goldfish. However, I don't really use the adult zebrafish. I use these guys. This is a zebrafish embryo, and there are several reasons why we use them in research. So firstly, they're completely transparent during development, which means if we want to know what's happening in the brain, all we have to do is just look and see what's happening. They develop outside of their mother's body. That means we have access to the brain in those very early stages, which is very important for a disease that affects children. And, very important as well, their DNA can be easily modified to reproduce patient mutations. That means when we find a patient with a specific mutation, we can immediately replicate that mutation in our lab and see how that affects brain development. When you put all of these together, you get a system, an elegant system that allows us to easily track the development of brain in health and disease in the patient context. So, what am I doing at the moment? I'm investigating a new type of leukodystrophy. So this leukodystrophy was identified for the first time in 2022, so 2 years ago, in a couple of siblings. Unfortunately, the younger sister died at the age of 3. The older brother is still alive, but is currently unable to walk or speak. Well, it started with 2 patients 2 years ago. Since then, we've identified 16 more patients, and we expect this number to keep rising as more and more facilities around the world are testing for this disease. And to tell you a bit of what we've achieved with the zebrafish model. So, a bit about this fish. It does something pretty cool. So, when the immune response is activated in this fish, the fish turns red. And what we've found is that when we reproduce the patient mutation in the zebrafish, the fish lights up. And this marks the very first thing we've learned about this disease. The immune response in this patient is activated. Now, I'm currently still doing research to understand the role of the immune response in the damage to the white matter. But if the immune response is behind the white matter degeneration, as it happens in several autoimmune diseases, this would be very easy to translate into a therapy. Because we already have drugs to target and activate immune response. Some of the very first drugs that we use for COVID, for example. And this really captures the vision of Leukolabs. 2 years ago, we identified the first patients. We are currently using our models and our research network to understand the disease, and we hope that in the near future, we'll be able to come up with a therapy. Lastly, just on behalf of everyone in the Hamilton Lab, thank you for being here today.
Okay, I think we're just out of time, so we'll wrap up there. I'd like to thank the speakers once again. Unfortunately, our professor of the director of the programme couldn't make it today, so he passed us on apologies, but our students did a great job showing, hopefully, why you're not dead by medical science and the impact that has. So thank you again, speakers, and thank you for coming down.